A sodium sulfate solution and barium nitrate solution are mixed together. Write the net ionic equation. So the first thing we want to do is we want to write the molecular equation for this reaction. We see that we have sodium sulfate solution and we have barium nitrate solution. So we'll go ahead and write their chemical formulas. So we got Na2SO4 plus Ba. Barium has a 2+ charge, so we need 2 nitrates. And that gives us what? Well, we see that we have 2 ionic compounds. So the cations are going to swap, so we get sodium nitrate and barium sulfate. And then we can go ahead and put on the physical states. It says that we have sodium sulfate solution and barium nitrate solution. So we can automatically write these as being aqueous, dissolved in water. Sodium nitrate, we see that we have a group 1 metal and a nitrate. We know that either of those is always going to be aqueous. And then we have barium sulfate. And if we look at our solubility rule sheet, we see that sulfates are generally soluble. However, barium sulfate is an exception and it is insoluble, so we're going to label this as being solid. And then we just make sure that this reaction is balanced. We have 2 sodiums here. We only have 1 there, so we're going to go ahead and put a 2 here. We have 1 sulfate, we have 1 barium, and then we have 2 nitrates, so we're good. So now that we have the molecular equation, we're going to go ahead and write the complete ionic equation. And for the complete ionic equation, what we want to do is we want to look at everything that says aqueous. And then all the ones that say aqueous, we're going to consider whether or not it's going to dissociate in water. And we know that if it's a strong electrolyte, it is going to dissociate in water. And we know that soluble salts and strong bases and strong acids are all strong electrolytes. Here we have some ionic compounds, we have some salts. They're all soluble. So each of these is a strong electrolyte. They're all going to dissociate. And then if it's a solid, a liquid, or a gas, we're not even going to consider that. They're going to remain the same. So when we write our complete ionic equation, we're going to split these soluble salts up into their ions. So we get 2 Na plus aqueous plus a sulfate aqueous plus a barium ion aqueous plus 2 NO3 minus aqueous. This gives 2 Na plus aqueous plus 2 NO3 aqueous. And then finally we have our insoluble salt. It's going to remain as a solid. Alright, so this is our complete ionic equation. Once we have written our complete ionic equation, we can go ahead and write our net ionic equation. And what the net ionic equation is it's the complete ionic after we delete all the spectators. So spectators are stuff that were present before and after the reaction, and we just have to make sure that they're also in the same state. So we see that we have sodium ions on both sides. They're both aqueous, so we can go ahead and cancel those out. We see that we have 2 nitrates on both sides, both of which are aqueous, meaning that we can also cancel those out. And that's all that we can cancel. So everything in red, we call them spectators. And then once we got rid of all the spectators, we can go ahead and write our net ionic equation. So our net ionic equation is sulfate ion plus barium 2+ ion yielding barium sulfate. Solid barium sulfate. And this is it. This is our net ionic equation. And this tells us that when we mix these two solutions, this is the reaction that's actually taking place. Alright, let's take a look at another one. This next one says that a small piece of magnesium ribbon is dropped into a solution of zinc nitrate. Like we did earlier, we're going to first write the molecular equation. So we got a small piece of magnesium ribbon. So we have solid elemental magnesium is dropped into a solution of zinc nitrate. So zinc is a transition metal, but it is an exception, and zinc is always 2+. So we got a zinc and 2 nitrates. And because it says solution, we know that it's going to be aqueous, and also it's a nitrate, so we also know that those are always going to be aqueous. And then we notice that we have a single replacement reaction here. We have an element that could potentially displace this cation here. And we know that for single replacement reactions, we have to use our activity series to make sure that magnesium is more active than zinc. And if it is, that means the reaction does take place. If magnesium is less reactive than zinc, then this reaction will not happen. So let's go to our activity series. So I have one down here. And we're going to compare magnesium, and we're going to compare zinc. And the activity series tells us that magnesium is more reactive than zinc, because here we got the most reactive, and on the other side we got the least reactive. Magnesium is further up the scale, so it is more reactive, therefore this reaction will take place. So when this happens, magnesium is going to kick zinc out. So we get magnesium nitrate, because magnesium also is a 2+ ion. It's going to be aqueous because it's a nitrate. We know those are always going to be aqueous. And then we have zinc that got kicked out, and that zinc is going to be solid. It's going to be just plain elemental zinc. So then we quickly make sure that this is balanced, and it is. So now we can go ahead and start thinking about writing the complete ionic equation. So we see that we have 2 aqueous compounds. We're going to see if they dissociate or not in water. And we see that they're both soluble salts, so they're both strong electrolytes, and therefore they will dissociate in water. The solids are going to stay the same. We have magnesium solid plus whoever this compound will dissociate, plus 2 nitrates. This compound will also dissociate. And finally, the zinc also stays the same. Alright, now before we write our net ionic equation, we want to look for any spectators. So let's look for something that's on both sides that are the same and in the same state. We see that we have nitrate. I forgot to put a minus charge there. We have 2 nitrates on both sides. They're both in the aqueous state, so we can go ahead and cancel those out, and those are going to be our spectators. And now we can go ahead and write our net ionic equation, which is magnesium solid plus zinc ion, giving us magnesium ion plus solid zinc. And this is the reaction that takes place in this statement. And what happened is basically a transfer of electrons. So this is a redox reaction. Something was reduced and something was oxidized. We had a transfer of electrons. Alright, let's look at another one. Gold metal is dropped into a beaker full of sodium hydroxide solution. So once again, we see that we have a solid element and it's being dropped into a solution. So we have to use our activity series to see if gold is more reactive than sodium. Our molecular equation would be gold, solid gold, plus sodium hydroxide is NaOH, and that's aqueous because it tells us so. So now we figure out if a reaction happens. So let's go to our activity series. And now we're going to compare gold, Au, and sodium, which is up here. So for this reaction to occur, the guy that wants to kick the ion out, which is gold, has to be more reactive. And we see that gold is actually at the bottom of the scale and magnesium and sodium is way up here. So when we go back to our reaction, sodium is way more reactive than gold, so this reaction will not happen. So we can go ahead and write no reaction. And if there's no reaction, there's also no net ionic equation that can be formed. Alright, let's look at one last one. So here we're asked to write the net ionic equation for when potassium acetate and hydrochloric acid solutions are mixed. So let's go ahead and write our molecular formula or molecular equation. The molecular formula for potassium acetate is KC2H3O2. That's going to be aqueous because group 1 metals are always going to be soluble. And then we have hydrochloric acid, which is just HCl. That's aqueous. We're going to go ahead and swap the cation ions. So we will get HC2H3O2 plus KCl, potassium chloride. Here we have acetic acid. That's going to be aqueous. Then we have a ionic compound here, KCl. That's also going to be aqueous because we have a group 1 metal here. Alright, now we want to make sure that everything's balanced and everything looks good. So we'll go ahead and write the complete ionic equation. And so we consider everything that says aqueous. We check to see if they are strong electrolytes. So the first one, we see that we have potassium acetate. It's a soluble salt, and all soluble salts are strong electrolytes, so this one will dissociate. Hydrochloric acid is going to be a strong electrolyte if it's one of the strong acids, one of the 7 strong, which it is, so this will also dissociate. Here we have acetic acid, and acetic acid is not one of the 7 strong acids, so this is not going to dissociate. And then finally we have KCl. This is also a soluble salt, so this will also dissociate. So now we'll go ahead and write our complete ionic equation. So we have one potassium ion plus an acetate ion plus hydrogen ion, chloride ion. The acetic acid is not going to dissociate because it is a weak electrolyte. And then we have potassium ion, and then I'm going to squish in the chloride ion. Alright, now we're going to look for spectators. We see we have 2 potassium ions on both sides. Those are spectators, they will cancel out. We also see we have 2 chloride ions. They're both aqueous, those are also spectators, they're going to cancel out. So finally, our net ionic equation is the complete ionic equation with all the spectators canceled out. So that is going to be acetate ion. There should be a negative charge there. plus hydrogen ion, giving us acetic acid, which is a weak acid and a weak electrolyte. And this is it. This is our net ionic equation.